All right, class. This video is going to walk you through back into Grasshopper, a short script that we're going to use to emulate some of the work that Chromatio and Kohler did with their robotic arm early on back in '08 and '09, a project called Structural Oscillations. This project eventually became an installation at the Venice Biennale, installed in a series of sections out of these typical modular units. We've talked about Rob, their deployable KUKA robotic arm that sits inside of a shipping container that was sent over to Venice to actually fabricate each of these pieces. The way that each of these went together was basically that Rob would pick up a brick, move it over to the nozzle here to apply some glue to the underside of the brick and then position it in place. You can see some of the foam blocks here were used, as well as some of the supports buttressing to support the walls before they were moved into the space at into the Swiss pavilion at the Venice Biennale. Here are some bricks on conveyors that will be really similar to the ones that we'll use. So you're going to, over the next week, write a script. This is the first part of that script that will program our KUKA robotic arm to stack bricks in a very similar fashion. It's very straightforward, surprisingly straightforward, simpler than maybe even creating a 3D print or running the CNC router or running the laser cutter. All of the components that drive the robot are actually built into a piece of software called the KUKA PRC, which is made by a group that was formed a few years ago called Robots in Architecture. We're going to be using their components to write the script based on a geometric script that we're going to work on today that positions each of the bricks in their appropriate location. Just a few more images here of that final piece inside of the Swiss pavilion in Venice. You'll notice that the bricks don't actually follow the tangent of the curve, but instead are pivoted out and rotated out to create this texture along the wall. And that's a very particular characteristic that we'll talk about today when we start working on our script. And here's a similar variation to what you're going to see. So working in Grasshopper this way, we're actually going to talk about how to write the script so that you're not actually deriving the shape from a given form, but instead allowing the form to be driven by the unit of the brick itself. So what we're going to start with is the brick size, and then develop the geometry, the constraints of the geometry based on that brick component. So if you don't remember, type in Grasshopper to load Grasshopper components. Moving back and forth between Dynamo and Grasshopper can be a little bit tough for a moment as you start to try to remember how the different components work, but they really work in very similar sorts of ways. So I'm going to split the screen here between the two and just create a perspective window inside of Rhino. I'm going to start off with some numbers, some number sliders, just to make it simple. I'm going to call one of these, the first one, length. And the length of a brick is 7 5/8 inches. So I'm going to put in 7.65. Oops, I need to edit my slider so that it'll go up that high. So I need to make the max. Go up to 10. And these don't have to be sliders. You could just put in regular numeric values. So length, and then I'll copy paste that twice to make width and height. The width of a typical brick is 3 5/8, so 3.625, and the height is 2 1/4 inches. It looks like I need to hit the check box. I'm sure I'm going to struggle a little bit moving back. Oh, there we go again. Moving back into Grasshopper here. Okay. Length, width, and height to start off with, and then the next slider that we want to do is going to be an integer slider. So we're going to, again, hit edit on this guy and change it over to an integer slider by clicking on the letter N here. And then we'll max out at, say, 20. This is going to be the number of rows of bricks. And by default, we'll just set this at something low, like 5 or 6. And then the last slider that we need is going to be one that can be variable, and it's going to be the gap. And it's basically just the gap, literally the gap between bricks moving horizontally across the row. And I'll turn this down to around something under an inch just to get us started. So these components here are basically going to serve as our inputs into this script. So what we want to do now is we can define a couple of pieces of geometry. We're just going to do 2 really simple curves. So just here in Rhino, I'm going to go to the control point curve and just give myself one S-shaped curve and one C-shaped curve. At the ground, a brick wall is going to be more stable if it's S-shaped, and so I'm going to leave that as the lower curve and the C-shaped one as the upper curve. These are basically going to define a lofted surface that then we'll use to derive the actual brick shapes. So the first thing that we need to do is move the lower curve. Well, we need to bring the curves in, so I'm going to put in 2 curve components, and I'm just going to copy paste. And I'm going to change the name of this first one to upper, and this next one to lower. And so again, the C shape is my upper curve. I will say set 1 curves, and then select the S-shaped one, right click on it, and say set 1 curve for the lower curve. The lower curve really isn't going to move. The upper curve, we're going to move this up in the Z direction, so I need a Z component for translating it. And the value that we're going to translate it up in the Z direction will be a multiplication. So I'm going to put in a multiplication component. It's going to be multiplication of the number of rows times the height of the brick, which was this 2 1/4. I need to go back and change these names. Height and width. And then that multiplied value goes into the Z. And I can see right away that my curves are huge. So I'm going to just, here in Rhino, scale them so that I don't have a ton of bricks that I'm dealing with all at once. This is sort of proportionate to a wall that is 6 units high. And then we're going to loft to create the surface between these 2 components. So between the one that we just moved and then this original lower curve. And I'm holding the shift key down. You can see that here the surface is twisted. This is caused by the fact that one of these curves was drawn from left to right and one was drawn from right to left. So here in Rhino, I actually need to just type in the word flip while selecting one of the curves, and that's going to actually flip the direction of that curve so that everything gets straightened out. Now what we want to do is an intersect, a B-rep intersect. This is going to be B-rep intersect. Let's see if we can find it here. It's a B-rep plane intersect. So to define a couple of these things, a B-rep in Grasshopper is a boundary representation. It's any solid or surface that you want to dump into it. And then the planes that we want to intersect it with is going to allow us to basically cut contours at the height of each of the bricks moving up through the script. So this B-rep is going to take this loft shape, and we're going to intersect it with a series of planes. We can create those planes really simply with a series. So we're going to create a series which is really just a series of numbers, of numeric values. The series is going to be defined by, it needs a start, which is going to be 0. It needs the number, or excuse me, the step size. The step size is going to be the height of the bricks. And the count is going to be the number of rows of bricks that we have. And if I plug this into the SEC, you can see it doesn't work like I thought it would. So we need to put a z component into this. Any point with a vector defines a plane, because it has a direction in the z direction. But my z component doesn't like parameter f, failed to collect data. Why is my series component not working? I'm going to put a panel component on this so that I can see what's coming out. So for some reason the series component started working as soon as I moved the slider. And you can see that these values that it's spitting out are 0, 2 1/4. It's basically increments of the height of the brick. And as I change, this is exactly what I was describing. The height of the wall is defined by actual brick heights. So the whole constraint of this system is driven by the proportions of the brick, the size of the brick itself. Now, as you move up and down, the number of rows increases and decreases with this slider defining the number of rows that you have in it. So now what we want to do is use a dispatch, which basically splits up the rows of components into two different conditions, because we're going to have one brick, obviously with any kind of typical construction method with a brick, they're offset by half the width of the brick in each row. So we need to treat the even and odd rows of bricks differently. So in this case, we're going to use the dispatch, which basically gives us every other row into a sublist. And then we're going to divide those curves by a distance. So I'm going to need two of these components now to deal with the even and the odd lists that are each lying inside of A and B here. So I'll put the two sets of curves, which are these curves generated over here, into the two components. The distance that we're dividing by is going to be the length of the brick, 7.65, plus this gap dimension. So I'm going to need an addition component to create the distance between each brick, which is not just the width, but also the gap. And I'm going to put that into the top one. Now, in order to get these bricks offset, what I'm going to do here with the lower set of this division is to actually divide, put another division component in, mathematic division, and take this value, and I'm going to right click and say set the data, set data to the number 2, and put that into this, so that I'm getting, with this division, twice as many points as I am with the division up here. So what it looks like is all of my components are going into one list because this needs to be flattened. So I'm going to flatten that list, and now you can see we've got twice as many in the even rows as we do in the odd rows. So then I'm going to use a dispatch component again to basically get every other one of those points into a sublist. And if I put a point container here, you can see which one we've got. So here we've got the ones that are staggered away from the start point. These are as well, so those are the incorrect ones. So from the letter B here, if I select both of these, now you can see that I've got points that are offset from one another, moving up the brick wall. So that's coming out of the dispatch of B. So the other thing that's really useful about this divide distance component is these tangent curves, which come out of each of them. And these tangent curves are going to allow us to do what's called a vector rotation. It is not that one. It's called VROT. is the component that you want to get. And this VROC component, when applied to the tangent, is going to allow us to pivot the angle of each of the bricks so that we get that kind of texturing that you saw in the Grammatio and Kohler version. So I need to emulate this dispatch with the tangents, because I've created twice as many tangents as I need for this lower components, which you might imagine is that these are the points, these are the tangents, these are the points, and these are the tangents for the odd rows, these are the ones for the even rows. So this VROC component is going to go on the B, coming out of there and out of the tangent here. So I've got the tangents for each of the two subsets. The rotation axis for these is going to be the Z once again. So I can make one Z and apply it to both. And then the angle, we're just going to make a slider with the number 90 in it. And these need to be converted into radians. So I'm going to make a radian component which converts the degrees into radians, which is what any component inside of Grasshopper that's doing a rotation is looking for. It's defined in radians. So while we want to work in degrees because that's what we understand, you're going to want to work, Grasshopper wants you to work in radians. So to get the actual locations for each of the boxes, we're going to use what's called a plane normal component. And very usefully, this is also exactly the same component that we're going to use to position the bricks with the robot. So I'm putting the plane and these rotated vectors into each of the plane components here. And what you're going to see now is that the planes that each of the blocks are oriented to are following the curve geometry, but they're also rotating as I move this slider around. So these planes will also, while we're going to use them here to actually position little bricks to represent and give a visual representation of what we're looking at. You're also going to use these exact same planes to tell the robot where to position the bricks in the tutorial that we're going to do following this one when we go to actually start scripting the robot. So you might imagine my laptop died just before I could finish this. So these planes, again, as I was explaining, are actually the planes you need for creating the box. And the brick itself we're going to make by using a box rectangle component. Nope, not a box rectangle component. We're going to make a domain box. So the domain box is going to be defined first by these planes. And you can shove both of the planes into both sets, and you can see by default it's creating a box there. And now what we're looking for is these dimensions. Let's not use a domain box. It's going to be messy. The domain box wants a minimum and a maximum from each of the points. Let's do a center box. There we go. Okay, so now when we plug the two sets in, you can see it gives us by default a 1x1 box, because there is a value of 1 in each of the XYZ components. Those are the boxes that you're visualizing. They're actually 2x2 because each of the dimensions is going in both directions from the center of the plane that we created. So the first thing that I'm going to put in here is to set an expression, which is going to be x divided by 2. And I'm going to do this for all three of the different inputs. Because our brick values are the full brick size, we're going to use this expression to ensure that we actually get bricks that aren't twice the size of what we want. And then I'm going to see if I can pan here. mouse got disconnected when the battery died. So if we can get this brick component over here, we'll finish this up. All right. So I think that the X direction is going to be the width. That's correct. And the height should be the Z. That looks correct. And the width then should be the Y. That is not correct. Let's try that again. So maybe the Z. There we go. Those look correct. So we've got the width of the bricks going into the Z value and the height going into the X value. That's because our planes that we see here are actually rotated. They don't have a Z value going up. Instead, they have a Z value going towards us. And so now you can kind of play around with this and change the number of rows of bricks that you want. You can change the gap inside of these, and obviously it gets a little sloppy if you go too big with the number of bricks that you have. But in essence, this script will give you a rough kind of approximation of what you want. The nice part here too is that you can always come into Rhino with this and grab a point and pull on it to change the shape of what you've got. And this is the top curve that I just changed, and you can see how the wall adjusts. Looks like we're having some little issues in there. Maybe we'll take a look at those. May have to do with the number of rows. No. Might have to do with our XYZ values. I'll take a look at that while we're getting that thing, and we'll talk about that in class. But you should start getting a variation of this that's similar in typical context. There's something fishy going on with the curves that I've got. Anyway, that's it for this structural oscillations tutorial.